Okay, our first speaker for this session is Corentin Bodart, who is at University of Geneva, who will be speaking on non-rationality and perhaps rationality of the complete growth series.
Yeah, thanks. So indeed, that's the title. Before I forget about it, all of this is joint work with Pierre Bagnoud, which is another PhD student here in Geneva. So what's the object for today? So we fix ourselves a finitely generated group and a finite symmetric set. So symmetric is just there to make things easier. And so if you have those two, this data, then you can deduce a word metric on the group. And so what's some object which is really classical to look at is the growth series. So it's a formal series with coefficient integers. And the coefficient is the number of elements in the group of length n. So you look at the number of elements for which the shortest way to write them as a product of generators as length n exactly. So that has been studied a lot. We look if it's rational, algebraic, or fundamental. Some people also look if it's finite or autonomic and other stuff. Here we're going to look at something which is a bit different. It's a richer growth series. So instead of just looking at the number of elements, we take as coefficients those an, which are the sum of elements of length n. And so it's an element in the group summary. And so the formal series at the end has coefficient in the group summary. Maybe you could ask why we take the summary and why not the group ring. That's a good question, but not for today. So what do I mean by rational and algebraicity, or rationality and algebraicity for those kind of series? So usually you just, in the usual setting, you just ask if they satisfy some linear or some polynomial equation for rationality and algebraicity. In this case, we're not working with a commutative ring as usual, but with a non-commutative summary, so it gets a bit trickier. So we have to look at systems, and the equation have to have some specific form. So I won't go more into details for this definition. I'll give another equivalent definition. So a series is rational if and only if there exists a finite state automaton, so something like this, with labels in the polynomials over the summary. So a finite state automaton is a finite graph with oriented edges. Each edge has a label, which is this polynomial. And then what you want, so you fix yourself two vertices, I and t, and you sum over all the paths, all the oriented paths from I to t. So maybe this path. And you sum the weight of those paths. So the weight of paths is the product of the weight of the edges, the individual edges. So for instance, for z, we take it to the cyclic group. We take the multiplicative notation, and we take the usual joining set. And this automaton recognizes the complete growth of this group with this joining set, and so that's proof that the complete growth is rational. So for instance, if I just take this path, then I get the term identity time s to the 0. 0, the exponent is the length of the element, so it's correct. If I take this path and go twice along this loop, I get x to the third and s to the third, which is the correct length again. So I get all the right terms. So maybe a small remark, as ng is generated by as a nth module, something like that, by g, you can always suppose that all the weights have the form just an element and then some power. Actually, you can even suppose that it's just generators and then some power. So that's something usually we prefer having the automaton in that form rather than just with polynomials here. So it's not that much studied. They're like, I don't know, max 10 papers on the subject, but it's linked with many properties. So the first one is admitting geodesic regular normal form. So what's a normal form first? So we have a group, generating set, so we can write elements as products of generators. And a normal form is picking exactly one way to write each element as a product, as a word over the generators. And then the adjective regular means that it's recognized by some finite state automaton. So here the weights are not polynomial, but just generators. Or we can also allow to have the empty label, which is the empty word, which is epsilon. So for instance, and then the certain automaton will recognize some language, which is again the set of words we can read along some path, oriented path, from I to T. So in that case, well, we have the direct path from I to T, which gives the empty word. Then we can maybe take this path and then try this loop. Then we're gonna read X, 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 and then nothing. So we get, choosing the left path, we get all the positive power of X, and then right path, sorry. And if we take the left path, we get all the positive power of X minus 1. And so indeed, this is there is exactly one way to word for each element of the group, which is Z in that case, which is the same as before. And then the last adjective is geodesic. So what we ask is that for each word in the language, so we have some length, and we want it to be, it's at least the length of the word, the element, because that's the definition of the word metric, and we want it to be exactly the word metric. So the word should be with minimal length. So that's a property. We can ask for a group with a generating set. And it does imply that the growth series is rational. All we have to do is to add next to each label, either S to the 1 if it's a generator, or S to the 0 if it's the empty word, and then we replace it by 1. And we get the same automaton actually that I just wrote on the slide before. So this is quite an easy implication. And then there is another property. So it's admitting a quasi-geodesic regular normal form. So it's the end of is the same. Quasi-geodesic means that for all elements in for all words in the normal form, the length might not be exactly the minimal length, but it's at most some constant times the length of the element represented. So there exists some constant, usually it's bigger than 1. So that the length of the word is at most C times the length of the element. So yeah, I wrote a bar on top of it to say that it was the element in the group and not the word itself. So that's a series of application. And then there's the last one. If the complete growth series is rational, then the same is true for the usual numerical growth series. So that's a bunch of properties. Maybe I'll say a word on algebraicity. So for algebraic, we should change in the previous slide with finite state automaton. We should change that with push down automaton. And then here we should change, so rational here by algebraic. Here we should change regular by unambiguous context-free. Same here, unambiguous context-free. Ambiguous. And so here again, algebraic. So it's really similar. And so in the previous slide, it was pushed down instead of just a finite state automaton. Okay, some questions about that we wanted to answer. So I'll just focus on 2 of them today. The first one is finding a pair, so proving that the having a rational complete growth series is really stronger than just having a rational numerical growth series. So we would like to find a pair, a group, and a junction set such that the numerical growth series is rational, but the complete one is not rational, or even not algebraic. And then the second question, it's actually a conjecture that's coming from, I believe it's Nagnimeda and so Tatiana and Slavagriorchuk. So they conjecture that if you have a nilpotent group, which is not a virtually abelian, then the complete growth series is always transcendental, so neither rational, but not even algebraic. So here we should always add non-virtually abelian, because it's known actually that if you take any virtually abelian group with any generating set, then the growth series is going to be rational. That's a result due to Liardet, which is another PhD student here in Geneva, but we're back. So the candidate group to answer the first question. So there are many, but the one we're going to focus on today is the Heisenberg group, the discrete one, of course. So usually you see that as the group of matrices, 3x3 matrices, with zeros below the diagonal, 1 on diagonal, and then integers on top. Here we're going to think about it slightly differently. So we're going to see elements of the group as equivalence class paths in the graph, in the grid Z2. So we drew two paths, and two paths are equivalent if and only if when you concatenate the first one with the inverse of the second one, so the second one backwards, you get a closed path. So here it's coming back. So this one is coming back at the end, at the origin, and you want it to enclose a total algebraic area of 0. So here, those cells are enclosed by the path. Those are the path goes in the trigonometric sense direction around it, so it's positive, and those one is like the anti-trigonometric sense direction. So those one are negative, and so if you sum everything, you get 0 area. And then something that's big theorem for standard growth series is that if you take any symmetric adjoint set for this group, finite, I should have added that, then the standard growth series, so the numerical one, is rational. And so we would like to prove that the growth series is, the complete growth series is not rational, and that would answer the first question. So that's what we're going to do. So I'm going to present 2 or 3, depending on how we count, obstructions to rationality of the complete growth series. So the first one going to be local obstruction in some sense, and then the second approach is more global. So the first one is what we call dead ends. So an element of the group is a dead end of some depth d if when you move not too far away from the, okay, you start from G, you move not that far away, so at most D, then you get to another element which is no longer than G itself. So if you take any small direction, so any small element in the group with length less than D, and you concatenate with G, you get an element which is shorter than G. So why do we call that dead end? The idea is that we want to run away from the identity and get to longer and longer elements. But if you get into a dead end, then there won't be any way to go further from the identity. So you have to go backward, and then you can maybe go to longer element, but you have to go backward sometime. And so an example of dead end in the Heisenberg group. So it's going to be this element G in blue. It's a large commutator. Okay, yeah, I forgot something. And so what I want to say is that this element is a dead end of some depth. Is going to be 4, I believe. So I take a short element. And what I want is to find another path, which is going to represent GH, so which is going to be equivalent to this one. So I want something which end up at the same point as GH. So it starts here and end up here, and it's grab the same amount of area as GH. So what I'm going to do is that first I'm going to observe that G is a commutator, so it's central. So I can take any cyclic permutation of it, and I still get another representative for the same element. So for instance, I could, instead of taking the path here, I could start the path at any point actually, and do that. And this is going to be another path that represents the same element, G. And so if I start here actually, and I stop here, I'm going to have just the right translation in the plane. So I'm going to have just the right endpoint. That's what I'm going to do first. And I stop here, and I have the right endpoint. Then I need to have the right area. And here, H grab the bit of area. So what I'm going to do is I'm going to move this cursor here, just so that I grab the right amount of area. And this element represent the same. This path, sorry, represent the same element as the concatenation GH here, and it's no longer than G. So this proves that the length of GH is no longer than the length of the path that represented here, which is shorter than the path here that represented G, which is optimal, by the way. Okay, so that ends in Heisenberg. We got that. And so the theorem, the main thing, is that if you have an infinite sequence of dead ends of increasing depths in a group with a Duchin set, then the complete Gauss series cannot be rational. And so here I just proved, I sketched that there were those large dead end in Heisenberg with the standard Duchin set. Actually, it's true with any finite Duchin set. That's the result of G2 Warshall in 07, I believe. And so as a corollary, you can prove that the Heisenberg group, the complete Gauss series, is not rational with respect to any symmetric Duchin set. So, okay, maybe two things I should say. That those dead ends, those are large commutators, so they are central. And so actually, you can prove a little bit more. The fact that those dead ends are central, so that implies, okay, you need more work. It's not actually not true, but it does half of the work to prove that the Gauss series is not algebraic. So the complete Gauss series is not algebraic. So complete Gauss series is not algebraic. So actually, we can prove that the Gauss series for the Heisenberg group with respect to any Duchin set is not algebraic. So this is half of it, and then you need some more geometry to do the rest of it. That's one point. And then the second remark I wanted to say is that it doesn't work for any nilpotent group. So you cannot generalize these arguments. So for instance, if you take just the direct product with Z, and you take Duchin set, so any Duchin set for the Heisenberg, and then you cross it with and you add just the generators for Z. And then with these Duchin sets, the product doesn't have any dead end, even of depth 1, because you can always find larger and larger elements just by adding some element of T. And so for that reason, we need something more. And this something more is what we call the Almol's almost saddle elements. And then there is two parameters. So again, there is depth, and then there is a margin of error. It's going to be m. So again, it's an almost dead end is an element of the group. And we want that for any small direction in the group, so any small element of length less than d, if you look both at the element gh, so you move slightly in one direction, or you move slightly in the other direction, those two elements have length that are equal up to an error of n. So why do we call that saddle element? If you think about the group, and then you graph over it the length of the element, you get some saddle elements. Okay, I should have added a picture of that. And then the result is the same thing as before. If you have infinite sequence of almost saddle elements of larger and larger depth and fixed margin, then the growth series cannot be rational. So that's quite easy. And the hard part is to prove that if you take any, again, non-virtually abelian two-step nilpotent group, then you have those sequence of almost saddle elements of a larger and larger depth, and you have to fix some margin, which depend on the margin is fixed. And so again, we can prove that the complete growth series is not rational for those two-step nilpotent groups. And then last thing, some more global issues. So we had those two implications with a regular normal form that they are either geodesic or quasi-geodesic. And here we can add something in between. So here we had that there exists some quasi-geodesic, so there exists some constants such that the length of the rod is no more than c times the length of the elements. And what we can do is that for any constant strictly bigger than 1, we can ensure that we can find some normal form, again regular, such that it's C quasi-geodesic. So the multiplicative mistake can be made absolutely close to 1. And this is nice because we can actually prove that if you have any three-step nilpotent group of rank 2, then there is no then there is some optimal constant, so that you cannot have any regular normal form which has this distortion of at most 1 plus epsilon, at most c. Sorry. So we needed, there is some optimal bound we cannot be below. Maybe there exists quasi-geodesic, so maybe only using this form is not enough. But so with this form, it's enough. So okay, maybe I'll give an ID. So we ask that the group is not virtually abelian again. So the quotient onto the abelianization is infinite to 1. So there is infinitely many commutators. All those commutators need to be represented in the normal form. So there is many of them. And so in particular, we can, when we look at paths in G, representing those in the normal form, representing those large commutators, and we project them on Z square, we're gonna find large and larger paths that come back to the origin. I'm doing improvement if I am, which is totally useless. Anyway, so we have those large commutators, those large closed paths, and what we can do is we can leave them back in the free group. And in the free group, we can show that they are not 1 plus epsilon quasi-geodesic. We can find some multiplicative mistake. And as this projection here is contracting, if we have a multiplicative mistake in the free group, then we have the same thing in the group we were interested in. So that's solved the problem. So for rationality, for all three-step nilpotent group of rank 2. And yeah, maybe you could go further. For the moment, it's what we can do. So we have like 2 directions where we can treat all the nilpotent groups. they're like a full quadrant of it, but yeah, and yeah, that's it. Thanks.
Let's thank the speaker. Are there any questions for Corentin? Okay, after no questions. So early in the slides, you mentioned that having a geodesic normal form implies that you have a rational complete growth series, which implies that you have quasi-geodesic normal form. Is it known, are there any groups that are known that have a quasi-geodesic normal form that don't have a rational complete growth series?
Yeah,
Is that
so actually I should have mentioned that. I can go back at this slide. Okay, I should have written all over. So yeah, there are. So for instance, that's something I forgot. So one way to show that complete growth series are rational is to have those regular normal forms. So here, for instance, if you take any hyperbolic group, you here, and then okay, I'm gonna answer your question afterwards. Here you have virtually abelian groups that are so that's what I said, but not all of them have geodesic regular normal forms. And then here we can add, I don't know if there's anything in between here, but here we can take Lamplighter groups. Lamplighter groups, the usual regular normal form, the most naive one you can think of is 3 quasi-geodesic, so you can take C to be 3. But it's not, the growth series is not rational because you have the dense. So that's the thing is what you were looking for.
Okay, thank you. Were there any other questions? I did have other things written. Oh yeah, I found it interesting, your definition of the complete growth series being rational. I hadn't seen that particular one before.
Yeah, so
is that like this? Is that a lesser known definition of rational numeric growth theory?
Yeah, so usually, I mean, this definition is quite usual when you work with languages and rational languages and rational series, but usually the okay, so it's a result of Trujan-Berger first, which is kind of old, but yeah, Pierre found that that characterization. I mean, found it later that characterization. Usually, so we look at something with a ring, a summer ring, and usually they take as variables non-competitive variables, and they take series, and instead of having only one variables s, they have a bunch of non-competitive variables, and the interest is in finding the support of the changing series. So like the coefficients are really not that important. And so there is a lot of work doing in that direction. But here we are like the set of variables, there is only one symbols, and it's commutative, and the support of our series is like usually everything. So we're really interested in but actually, so the term is also useful to look at the coefficients, even though it's not really the point usually in the literature. But it's yeah, I think if you work with like series and non-commutative variables, it's something that's quite common. Otherwise, probably we don't know.
Okay, thank you. So I don't think we have any time for any more questions. So let's just thank Corentin again.